The purpose of this chapter of the video series is to describe what manufacturing modeling logic is and why it's relevant to both finance and operations. This video answers 4 questions about integrated and manufacturing specific modeling logic. What is it? Why do you need it? What happens when you don't have it? And what processes are affected? The first thing we need to do is define what we mean by integrated and manufacturing specific modeling logic. Provided on the screen are examples of logic that comprise manufacturing models. Terms such as bills of materials and routings should be familiar to those working in the manufacturing sector. You'll get a sense for what they entail in the video, but if you want more detail, you might want to educate yourself on them. The main thing to take away from this slide is that strategic, financial, and operational processes all share this logic. Let's start off with a simple example. Provided on the screen are bills of materials for 2 products, P1 and P2. Bills of materials are typically expressed in hierarchical form, as shown on the screen. A bill of material is a list of product components. Here's a simple analogy. If you are baking a cake, a recipe defines the ingredients to make it. This is equivalent to a bill of materials. The instructions that define the steps for using the ingredients is equivalent to what's called a routing. So getting back to the examples on the screen, the only difference between the two is that product 1 uses component B, while product 2 uses component E. Next, let's talk about planning bills of materials. They're used exclusively for planning, and by definition, they're not actually something that can be made. In this case, the product 12, in the red box at the top, represents a product family comprised of products P1 and P2. Demand is planned at the product family level and then distributed to component products by way of the planning BOM. In this case, 70% of the volume is attributed to product 1, while 30% is attributed to product 2. The idea is important to understand as we discuss volume and mix changes in later slides. Planning bills of materials can also be used for purchase parts. On the screen, you'll see the components B and E are comprised of the same purchase parts, except that B uses purchase part 3, while E uses purchase part 4. At the next level down, we see that purchase part 2 is supplied by 2 different vendors, X and Y. The only difference between product 1 and product 2 is that the amount supplied by vendors X and Y is different, as denoted by the boxes on the bottom row. For product 1, it's a 50-50 split, while for product 2, it's a 40-60 split. Next, we introduce economic differences between the vendors. Purchase part 2 costs $10 from vendor X and $12 from vendor Y. This is denoted by the light blue boxes on the top left. There's also a difference in how the 2 parts are used in the production equipment. While the part from vendor X may cost less, it takes a half-hour longer in production. Conversely, vendor Y costs more but takes half-hour less in production time than X. This is denoted by the dark gray boxes on the top right. This screen shows how these inputs are used to calculate both costs and production requirements relating to purchase part 2. Differences in vendor allocations result in different average purchase costs. For product 1, the average cost is $11, while for product 2, the average cost is $11.40. Now these same differences between product 1 and 2 also result in different average production costs as well as average. Now let's consider the impact of a change in sourcing mix, where vendor X is used exclusively in product 1 and vendor Y is used exclusively in product 2. You can see how the average costs and hours change at the bottom of the screen. Now, let's consider how batch costs are affected by sourcing mix changes. Examples of batches are production setup and inbound transportation costs. They are the same regardless of volume in the batch. In this example, we'll use transportation costs. At the bottom of the screen, you'll see the transportation costs expressed in terms of cost per shipment and lot size being the minimum order or shipment size. Now, assuming the vendor allocation shown in the pink boxes, the impact on average purchase costs is shown in red. Now, let's assume the vendor allocation changes to the percentages in the white boxes. You can see the impact on transportation costs at the bottom of the screen. The point here is that these types of changes complicate the process of quantifying how costs will behave and their impact on standard and average unit costs. Changes in vendor allocation also affect cash flow forecasts. Consider the vendor allocation shown in the green boxes. For product 1, all purchases of purchase product 2 are coming from vendor X, and for product 2, all purchases of purchase product 2 are coming from vendor Y. At the bottom, the impact on cash outflows is shown for both vendors X and Y, each of whom have different payment terms. Now consider how forecasted cash outflows change when vendor mix changes, as shown in the pink boxes. Forecasted cash outflows are now a mix of the vendor payment terms of both vendors X and Y. The point here is that the ability to forecast the physical flow of goods is essential for effective cash flow forecasting processes. Let's look at the cash flow example again, but now assume that vendor X is paid in euros. Our starting point is that all purchases for product 1 are coming from vendor X, and all purchases for product 2 are coming from vendor Y. This is denoted by the green boxes. Now we see what happens when mix changes, as denoted by the pink boxes. You now see that there are euro payables for both vendors X and Y. Such logic provides the means to forecast both cash flow and foreign currency exposure. For treasurers, such forecasting capabilities can be very important. In the examples shown so far, we've touched on a few simple changes, but consider all the ones that can transpire from one period to the next. These could range from demand volume and mix changes to new products, routing, and bill of material changes, and there could be scores of other changes all taking place simultaneously. As manufacturers become larger and more complex, it becomes increasingly difficult to cope with these changes. Embedded modeling logic is a tool for coping with them. One of the biggest advantages in having such logic embedded into an application is that it provides the means to distribute ownership of the model across an enterprise. When finance and operations have different processes and tools, finance must maintain the models that it uses for planning, budgeting, and forecasting. This usually is a manual process whereby financial analysts identify material changes to operational models. In an integrated environment, this task is shared with operations. For example, a buyer that works with a single vendor might be responsible for maintaining vendor allocations, pricing, lot sizes, and payment terms. And there may be 50 other buyers doing likewise for other vendors. Outside of buying, there could be hundreds of others maintaining other parts of the model. The point is that finance doesn't need to do this. The model structure provides the means to share this responsibility for maintaining the model with operations. For such manufacturing logic to be useful, it must be able to support operationally realistic models. This means 4 things. First, it should support multiple model versions. There could be one for a budget, one for a forecast, and others to support different scenarios. Second, models should be time-phased. This means that model parameters within a version can vary from one month to the next. And this is important to reflect changes in operational capabilities and constraints. Third, it should support mass model changes. For example, this is essential for coping with actions such as replacing one vendor for another, or changing vendor allocations as we saw in the examples. And lastly, it's important to execute these models across legal entity. This is important for a company that has multiple plants that work interdependently. The ability to support such modeling logic dramatically improves many financial processes, examples of which are shown on the screen. Conversely, their absence can significantly impair the ability to forecast cash flows, foreign currency exposures, value-added tax, and commodity hedging positions. Moreover, these gaps also impair the accuracy of financial forecasting and scenario planning processes. In other words, these gaps can be significant. Some finance professionals might question why they would want to have such detailed logic in a planning system. Their question is it really worth the effort? Now, in larger organizations, you probably don't want such detail. In smaller manufacturers, it might be easier just to use the detailed models straight out of an ERP system. However, in larger manufacturers, this will likely involve too much detail and effort. That's where aggregate models come in. The point here is that manufacturing-specific systems provide the means to support either approach. and to enlist the support of the organization in maintaining these aggregate level models. The most obvious impact of capability gaps is that plans and forecasts can be inaccurate. What's more, the models used to develop them can be costly to maintain. When financial and operational models aren't integrated, it falls on finance professionals to maintain them. And when there's a lot of change, it takes a lot of effort to update them. Even if they can be maintained, it may take too much time to do so. The result? The information isn't there when it's needed. What's more, the absence of transparency between finance and operational data can impair its credibility. Integrated and manufacturing-specific modeling logic addresses these issues, which are now highlighted in red. But it also accomplishes other things. It reduces the time and effort to implement and maintain these models. It minimizes risk and complexity. It enables organizations to adapt to change. And it also enables more effective frontline ownership of models and results. There are 4 key takeaways from this video. It's that integrated and manufacturing-specific modeling logic enables financial processes that have 4 key advantages over other modeling approaches. They're faster, they're more accurate, they're easy to maintain, and they have a lower cost of ownership. Thank you for watching this video. Further details about its contents can be obtained using the contact information provided on the screen.